All right. So first of all, thank you very much for having me here, Josef, Lucio, and also Christian. And it's a pleasure to be at this conference. Sorry about that. This is joint work with Andrea, who is here, and then two former students from Hong Kong U, Sining and Yayan. So in our paper, we basically start with the seminal paper by Lustig, Roussanov, and Verdelhan on the dollar factor, which is borrowing US dollar and lending in all the other currencies equally, and the carry factor, which borrows in low interest rate, lends in high interest rate currencies. And they have shown that these two factors explain very well interest rate sorted portfolios or returns of interest rate sorted portfolios. But then, of course, there was a big literature evolving showing that if you sort currencies in other ways with other characteristics, then these two factors don't go very far. And of course, half of that literature was written by Lucio, and most of these papers with people in the room together with Lucio. So now, one problem with the literature, I think, is that these tests are usually done in an unconditional setting. So basically assuming that in the estimation, factor loadings are constant and risk premia are constant. Now, of course, not all the papers do that. Usually when people try to estimate something conditionally, they use a set of conditioning variables, but then there's always, of course, the concern, do you specify that set correctly? Does this really capture all the dynamics or not? Now, we try to look at this again and basically ask the question, well, if we look at this time series variation in factor loadings and risk premia, can this actually help the dollar and carry factor, two-factor model, to price the cross-section better, yes or no? And of course, the answer will be that we find that actually you can go quite far if you do that. In our paper, I think we also have a small methodological contribution. We kind of show how to estimate this dollar carry factor model, conditional model, by not having to specify specific conditioning variables. And we also show how we can do this in GMM, which is actually a setting which is quite similar to the standard one, just some minor extensions, but I still think it's nice. Let me just show you the results on one slide. So basically, if you do the unconditional model, where the return on the left-hand side is basically dependent on the factor loading beta times the risk premium gamma, and that stuff is constant. And if you do this for a set, this is for 27 test assets, you see that basically the predicted returns in the model versus the average returns in the sample, there's really nothing explained, right? So these test assets, if the model works well, should line up on that 45-degree line. Obviously, they do not. And R-squares are basically 0. If you do a conditional version of the model, so where you allow these beta, these factor loadings, to be time varying, and also the risk premium gamma, now with a time index t, to be time varying, and we basically use, when we test it or implement this in the data, we use a trick which goes back to Jagannatham and Wang in 1995. You take expectation of the conditional model, and then you basically, what do you get is an expected factor loading times an expected premium. So that looks almost the same as the unconditional model. But the interesting part is that covariance between the factor loadings and the risk premia. And that's really the key piece which we point out in our model, that covariance term. Once you account for that, once you introduce that into the model, then things line up super well. Okay, so basically all these deviations here eventually go back to that interaction between this time series variation in factor loadings and risk premium. And your R-squared is super high here. Now, where do I see the contribution of our paper? I think they're really, well, there's this small methodological thing, which we'll talk about it later a little bit. But I think there are really three big, important implications. The first thing is, from an empirical point of view, of course, there were all these other characteristics, right, which people rightly have shown. They seem to explain, or you sort on these characteristics, you get very large average returns in an unconditional setting. What do we do with all these characteristics or these portfolios? I'm not saying that they are useless. it's actually the contrary. If you think about these other characteristics, they just should be reinterpreted in another way than what the literature thought before. So they're not really spanning a new risk space, but they're actually useful characteristics to help us understand this time variation in risk loadings. Okay, so that's the first thing. And together with this also, what I would hope to see in empirical research going forward is that people basically try to estimate these models conditionally and basically, estimating or using this covariance between beta and gamma in these tests, because I think this is a really important step which we should take. Now, of course, this is not completely new because the literature has evidence. I mean, there's a recent paper by Lucio as well where he shows that you can, from the space of all the factors, you can reduce a lot of it to essentially 2 or 3 factors. There is also another literature which basically says already that conditioning information is very important, right? Basically hinting at that there should be some kind of time series variation in risk loadings and premia, which is important, and we're kind of contributing to that. And I think in some sense maybe just show another step that this is like really a first order importance which you have to consider. Now, there's also another contribution, and this relates to a recent paper by Chernov, Dahlquist, and Lochster. Actually, they have 2 papers, one already published, one is a little working paper. And so they're building this mean variance optimized portfolio, actually very similar to one of my own papers I have. And they're saying, look, this identifies the SDF in FX markets. And then the second thing they do is they run regressions of test assets on their mean variance optimized portfolio, this UMVE portfolio. And they show that the time series R squares is close to 0. And they're then saying, well, that means that basically most risk in FX markets is unpriced. Okay? Now, I think I have some issues about that. I don't know how many of you have been at the WFA, but I discussed their paper there. So the first issue I have is their factor works really well for these small cross-section of test assets, which they look at in the paper. If you introduce a bigger cross-section, it actually doesn't work that well. So I think there's an issue that it doesn't completely identify the SDF. And so maybe that undefined or the dimension which is not captured could actually explain more of the cross-section. But I think the second thing, and I think a lot of people in the literature look at that as well, they say, look, if you look at the dollar factor, on average it has basically a 0 return, right? And so then people say, okay, whatever, the dollar factor is basically unpriced risks. But I think if you now take this view that this time variation is very important, and what you should think about the dollar factor is really like the risk premium is sometimes positive, sometimes negative. On average, it is 0, but really conditionally, this is a priced risk, and it is important. And so then if you think about really doing, again, time series regressions of test assets on dollar and carry, and if you believe that dollar and carry more or less, or at least capture the first order importance of the SDF in FX markets, then actually these R squares are really high. Okay, they are somewhere around 80, 90%. And so my conclusion then from that would be actually opposite. So basically, most risks in FX markets is priced, and that also goes actually back to theory, where exchange rates are ratios of SDFs, and naturally these risks should be priced. So we're kind of restoring what people believed a long time ago, or what theory tells us. And the last thing is, I think our implication where we show that really these time series variations in premia and loadings are first order, they have very important implications for theory, and in particular like macrofinance models. Right, so if you think about macrofinance models, and Rick can probably tell us a lot about that too, most of the time you're trying to match unconditional moments. And I think this literature has progressed a lot and can explain a lot about interest rate differentials and risk premia. But I think the new challenge will be try to look at this time series variation of risk loadings and trying to understand that a bit more. So in the following, I want to show a few more details about our estimation, which is maybe also the small methodological contribution of the paper. So the first question, of course, is how do we estimate beta, and then how do we estimate this covariance between beta and gamma? For the beta thing, we basically don't want to, for beta and gamma, we don't want to specify conditioning variables, because otherwise everything which we test will be dependent on what conditioning variables have we initially chosen. So we are trying to do as model-free approach as possible. And for the beta, we use daily data for, I mean, it's an exponentially weighted moving average, but essentially it's the past like 6 months of daily data which are important. And we look at the individual currencies and estimate the covariance matrix of all these currencies based on the daily data. Once you have the covariance matrix, this capital gamma, then all you have to do is you basically look at the portfolio weights of your traded factors, dollar and carry in our setting, and the portfolio weights at time t of your test assets. And essentially here the beta will be the covariance between test assets and factors, which again depend on these portfolio weights and the covariance matrix of the currencies, divided, or the inverse of the covariance matrix of the factors. So here, you have basically a very easy way to get this conditional beta. Of course, the challenging thing is how do you estimate the covariance matrix? And actually about 10 years ago, Pasquale told me this in one of his discussions of my papers. This can be really hard to do. We use an approach which I used in previous papers, where we use exponentially weighted moving average and using principal component analysis to try to estimate this robustly. Of course, I'm not saying that we do a perfect job with the covariance matrix, but when I talked to Lars last at WFA, he also had to admit the way they estimate it also, is not as good as they wish. Typically, you see this if you do a mean variance optimized portfolio, whether you use their approach or ours, you get like a predicted variance of your factor. Usually this is quite way off of the actual realized variance. So I know this is not perfect, but we try the best we can. Now the second question is, how do you compute now this covariance between the betas and the gammas? Right, again, if you think about the literature, typically people would now come and say take conditioning variables and basically do a projection and try to, or in other words, try to find the functional form of gamma depending on these conditioning variables. We say again, we don't want to do that because this kind of restricts ourselves. And we use another way to estimate that, which I think is quite simple, but I think quite powerful. We actually look at the covariance between beta at time t and the t+1 realized return of the factor. Now, what's the idea here? Well, if you think about the factor t+1 return, that's the premium at time t plus some surprise. And the surprise, of course, is not correlated with any information at time t. So it's not correlated with beta either. And therefore, that covariance between beta and the epsilon t+1 is 0. And so you get a consistent and unbiased estimate of the covariance between beta and gamma. Okay? And so again, there's basically no assumptions we need to do about specifying gamma at all. Okay, so we just take the data with t+1 returns. Okay, now how do we do then the GMM? So basically you estimate the average return of the factors, you estimate the average beta given the time series of beta which you have estimated, then you estimate this covariance, the sigma beta gamma, that's the covariance between beta and gamma in the entire sample. And then the key thing is this cross-sectional regression, right? Here you basically regress average returns of your test assets, the cross-section, on the average factor loadings, beta bar. And then you can either regress it on this covariance between beta and gamma and treat delta as a free parameter, or you can just impose that delta is equal to 1. Actually, if you let delta to be free, there are some power issues with this estimation. So for the most important parts of our paper, we just set theta equal to 1, and then you get a lot more power. But that's essentially our estimation. Then what are the testable restrictions? If gamma is not forced to be equal to the average return of the factor, then you can test, is this equal or not? We find that they're very similar, so whether you impose it in the estimation or not doesn't really matter. And then, of course, you can look at the cross-sectional alphas, right? The average return of the test asset versus what the model implies. And again, for most of the tests, we just set delta equal to 1 as theory predicts. Okay, I think the data, I don't really have to say much about it. It's kind of the standard stuff which people use. We have a set of 29 developed emerging countries from the mid-80s until very recently. Dollar carry factor I talked about already, and then we have here a relatively broad cross-section of test assets. Actually, we are working on, but it's not yet in the paper, which we gave to the discussants, on a bigger set of test assets, and these results will be available soon. If you remember the picture before where I showed you this cloud of points which cannot be fit with the unconditional model versus where it lines up very well with the conditional model, this is basically the numbers to that. So we find that in the unconditional model, this one here, you estimate a dollar risk premium which is insignificant, which the literature usually shows, carry risk premium which is large and significant, but you also find that actually these estimated risk premium are different from the average returns, which is already a rejection of the model. But most importantly, if you look at that, basically the GRS test, the alphas in the cross-sectional regression for the unconditional model, they're very far different from zero. Okay, so basically the model cannot explain these returns. On the other side, and the R-square model predicted versus average returns is basically zero. The conditional model, again, you find that the dollar risk premium is close to zero, and actually the risk premium estimate in cross-section regression is basically the same as the average return of the dollar, so it's only like 0.07% different per year. The risk premium of the carry factor is large and significant, and again, it's not statistically different from the average return. And then the most important thing is here, the joint test of are all the alphas in the cross-section different from zero. You cannot reject that. Okay, so basically the model does a good job. And then, of course, also the model predicted returns versus average return, they line up very well. So there was like these pictures, everything is in the 45-degree line. Okay, thank you. We can also look at basically like if you want to think about Fama-Macbething, the time series regression, we can also look at the average return of test assets versus average return of test assets minus hedging out dynamically these dollar carry risk. And so we contrast this on left and right hand side, and what you see is that like where you have significant average returns of a test asset after hedging out dynamically and in real time these dollar carry risk, basically your average returns go to close to zero. Some of them are not exactly statistically significant. This is a mean variance optimized portfolio, but you still go a far way from about 9% to less than 3%. So I think it's quite impressive to find that. The last thing I want to say is in our model, you have crucially this time series variation in risk premium, right? And so, of course, you say, well, if there's a lot of time series variation in risk premium, that would also imply a very high R-square in like predictive regressions, right? Because you basically have the return can be decomposed into surprises and risk premium. Now, we can basically back out from our estimates how much time series variation is or should there be in risk premium and translate that into how much R-square can you potentially get in predictive regressions on the dollar and the carry factor. And depending on how you do this, we find that R-squares would be somewhere between 3 and 7.5% for dollar, and for carry between about 2 and 4.5%. I think these numbers are quite reasonable, especially for dollar, where we know that like average forward discount can actually predict quite a lot. So I'm not too worried about that. I would have one more slide talking about the Chernoff, Dahlquist, Lochte, but I guess saved by the bell. So refer to my WFA discussion on that. Okay, conclusion. So we introduce a kind of novel GMM estimation setup where we show how to estimate this model in a conditional setting. And you don't need to specify state variables. Then we show that the estimated conditional model does a very good job explaining quite a rich cross-section compared to the unconditional model, and basically stressing this whole thing that conditioning information or this time series variation in risk loadings and risk premium is first order of importance and cannot be ignored. And then again, broader implications is that basically most FX risk seems to be priced once you account for these conditional models, because especially the dollar factor is actually an important thing, even though unconditionally it doesn't look like important, but conditionally it is. And then again, this is basically a new challenge which macrofinance literature has to tackle, or new moments which we can try to match. All right, thank you so much, and I'm looking forward to the discussion.
So thank you very much. I'd like to thank the organizer for giving me the opportunity to discuss this very interesting paper. So motivation of the paper is simple. Thomas explained very well. So we start from the seminal work by Hanno Lustig, Roussanov and Verdelhan, 2011, the common factors paper, and actually also previous work by Hanno and Adrian. And in their work, they find that you need two factors to account for the cross-section of currency premium. The two factors are dollar, which is a level factor that on which all currencies basically load equally, and then there is the critical factor to explain the cross-section, which is the carry factor that is capturing the return of a strategy that goes long high interest rate currencies and goes short low interest rate currencies. So basically the return from the standard currency carry trade strategy. In their work, the test assets are currency portfolios formed on interest rate differentials. Okay? What are the implications of this important work? Well, the SDF of the investors must be characterized by one global shock and then a US-specific shock. Foreign investors, SDF, differ simply in their exposure to this global shock, and carry capture indeed this global shock. Now, since this paper, a lot of work has been done by a lot of people in this room that shows that dollar and carry cannot account the cross-section of alternative set of test assets, value, momentum, in the currency space. Whereas additional currency factor can. Okay? So I think this is similar in a sense to the literature on the factor zoo and anomalies, for example, for equities. Okay? And if correct, it implies that the SDF actually must be characterized by more than one global shock. But the caveat is that the empirical literature typically uses unconditional asset pricing model of this kind, in which the expected excess return, unconditional, is equal simply to beta, quantity of risk, and gamma, if you want, the risk price, where if we use tradable factors, the risk price is simply equal to the mean of the factor, the unconditional mean of the factor. Now, note that actually the same paper by Lustig, Roussanov, and Verdelhan, they actually also consider a conditional model in which both risk prices and loadings are time varying. They do two ways with managed portfolios and actually with rolling windows. But of course, they only look at the test asset, the portfolio sorted by interest rate differential, and they do not consider all these other test assets. Now, these papers consider instead a conditional model with two factors, dollar and carry, and now risk loadings are time varying. The way I see it is that the main contribution are the GMM empirical strategy to estimate this conditional model, the fact that dollar and carry account for this rich cross-section of currency premia, including portfolios that motivate this novel, if you want, additional currency factors. And they also show that models based on alternative factors are rejected in the cross-sectional test once you use this conditional model. What happened here? Sorry. So what is the conditional model? Okay, it's very simple and nice. So you start from the equation up there that says that the conditional expectation of the currency excess return is equal to beta t gamma t. So now both the quantity of the exposure and the risk price are time varying. Okay? And the unconditional model is just, if you want, a special case in which both beta and gamma are constant. Okay? Now, what Thomas and co-authors do is the following. So they start from Resulti, Yaganathan, and Wang. Basically, they take the unconditional mean of that conditional model. Okay? So if you do that and you use the definition of covariance, you can break up the equation in the first line as you see in the second line. And now you have the sum of two components. Okay? So you see the first component is it's a beta times gamma that resembles the unconditional model, but it's actually different because the beta bar is not necessarily equal to the, say, the average of the beta. Okay? And then you have the second component, the sigma beta gamma, which is capturing this covariance between this time-varying beta and the time-varying risk prices. Okay? What the authors show is that the covariance part is really crucial for the result. It's the component that really is able to price the cross-section, this rich cross-section of currency portfolio, and that covariance, of course, shows up only if beta are not constant. So what is the interpretation of this covariance term? If you think about it, you suppose that you have an asset that has a higher loading on a given factor when also the factor premium is higher, which maybe we can think of, say, bad times, then the sigma beta gamma would be greater than 0. And so in that case, the unconditional model would underestimate the risk premium of that asset. Okay? Note that as I was mentioning, the beta bar is typically different from the unconditional beta. So this potentially could also be a source, to explain the result, but the paper showed that it's less important than the sigma. To estimate the model, so they use some sort of weighted rolling regressions to estimate the betas. Then they feed these betas in the GMM model that you saw in the slide a few minutes ago, and that's basically how the model is estimated. As test asset, the author used currency portfolios that are formed originally from 29 currencies, more or less split in developed and emerging currencies. And these are classic portfolios, starting from the classic interest rate sorted portfolio of Lustig et al. But then you have also momentum, value, FX correlation dispersion, dollar beta, plus two factors, the DOL and the CS carry. Okay? Result in one slide. Thomas showed this slide, this picture. You see that predicted and average return line up very, very well. The R square is 89%, whereas it's only 2% for the unconditional model. So I'm going to have two sets of comments. I'm going to be very, very brief. Okay? So the first is related to the time-varying betas. Okay? So for equities, we know that the advantage of using diversified portfolios is that you have more stable loadings. Whereas if you use individual equities, you have a lot of variation. This is a comment done by Pham and French in the 1992 paper. Now, the cross-section of currencies, of course, is much smaller than individual currencies, much smaller than that of equities. So it's very plausible that time variation in the portfolio load is more important than for equities at the portfolio level, because you cannot really diversify very well idiosyncratic risk. And actually, even in the equity literature recently, there is interest in variation in portfolio weights. For example, you can have a look at the IPCA methodology of Kelly et al., which basically has time-varying betas. Okay? In terms of comment here with respect to this, I would like to learn more about these loadings and their correlation with respect to the time-varying risk prices. For example, what is their persistence? I see there is a table in the paper that shows that are very volatile. So what about their persistence? What about the correlations with the macro factors? And what about correlation with interest rate differential? So a lot, the main result comes from the time variation in these betas. So I think I would like to learn more about their characteristics. Second comment, so the test assets include, as I was showing, two basically factors, okay, the DOL and CS-CAR, okay. I think it could be useful to add among the test asset also the other factors that people have used in the literature, okay? And I would like to know if they are priced by the conditional two-factor model, okay? And a related question is, how should I think about this additional factor? So if you read the paper, there is this sentence, additional factors in the literature do not give rise to new risk. In a reduced form, no arbitrage model, but they provide important information about the time variation in the factor risk premium and factor loading of the test assets. So is there a formal test for this statement? Perhaps these time varying betas, they capture time variation in the loadings of some of the test assets. So this is, I think, not really well spelled out in the paper. Could be spelled out better in the paper. And finally, if the additional currency factor have a significant premium, are they spanned by some combination of the dollar and carry? And if they are not spanned, should we think of them as anomalies? So I think these are all things that can be done and would be interesting to read about. So to conclude, excellent paper, which shows that two factors, dollar and carry, account for the cross-section of currency premia. The key is this conditional versus unconditional model, double empirical strategy to estimate the conditional model, and I think that the results carry important implication in terms of how to design the SDF. My comments, mostly food for thought, perhaps for future work. Thank you very much.
So thank you very much for the nice discussion. So I was already nervous, but you were very kind to us. So the first thing I think which I want to say is this is very interesting, and I would like to do more on that, and probably we should already do it in this paper to understand a little bit more these movements in these betas. It's very well taken, and definitely also there is definitely probably follow-up work which has to be done because I don't think we can answer that question completely. About the other comments, so I think here we kind of just, it's kind of implied by what we do, right? So if you think about, you have the dollar carry model and you do this unconditional estimation and you see that like some other characteristics, lead to alpha. But then once you use that covariance term, that covariance basically explains the alpha, then I think that means that these characteristics capture this time series variation of the factor loadings and premia, and especially how they covary together. So I don't think, if you have an idea how to more directly test that, I would be happy to, but yeah, it is kind of like indirectly implied, I think. But I would be open to test more if you give me some ideas how to do that. Yeah, I think that's the most important thing which I wanted to say. And there is actually some work. I mean, for example, Xiaochun Zhang has some nice paper which shows or argues that time variation risk premium of carry and dollar can, for example, explain momentum in FX markets. So I think this goes a little bit in our direction as well. Maybe that's a paper which provides a little bit more direct evidence for that specific momentum factor, which, yeah, again, ours I think it's more like indirect. Yeah.
Thank you. Time for questions. It seems like, sorry. I'm going to be quite harsh. It seems like the paper is almost a mathematical tautology, because once you say dollar and carry as a PCA explain 90% of the correlation of the volatility of FX returns, which is true, then what you're doing essentially is transferring, like any random factor, when you do the covariance structure that you're doing, basically transfers this to the loading of that factor on those two most volatile factors in returns, and that explains it. So it's almost like a mathematical, anything, even if you use any random strategy or anything like that, once you project it onto the covariance, it's just a way of rephrasing the problem, and you're going to get that explaining 85% of that strategy returns. So I'm not. I don't understand. Like, where's the added value here? Because what you're essentially doing is saying, carry and dollar explain 90% of the volatility, and I can project the returns of anything onto those factors with these two numbers. You know, the beta on these two things.
Okay. How should I answer that? So, okay. If you talk about the time series variation, right? That's basically you demean that and you look at the variation in the time series, and that can be explained by whatever factor. Whether these factors are important to explain the average returns, I'm not sure whether this is true. I mean, to the extent that every risk is, or all of the average returns is a risk compensation, then maybe in a conditional sense, this might be true, I don't know. But yeah, I don't think that's... But you're saying that only is true in a conditional setting, but not unconditional?
I'm just saying, like, sorry, I'm not sure about conditional versus unconditional. I'm just saying that if you have a time varying factor, okay, which is like, you know, norm, value, whatever, but once you project it onto the two, it will project necessarily into correlations to the two big factors, the ones we carry. And once you've done that out, reflected it out, the returns of that factor will disappear. The volatility just disappears structurally. And that means that's what you get there. Because like there's no, that's why you get such a thing. I mean,
I'm skeptical about that, because if you do like generally a principal component analysis, I mean, do that in equity markets, for example, even if you get a set of principal components explaining a lot of the time series variations, that doesn't mean that you can explain the average returns. I think because a lot of risk might be not the first few principal components, and that risk is really important for pricing. So I don't think that is mechanically directly implied. But yeah, I'm happy to talk more about this, and maybe can write it down. And yeah, but
yeah, I was wondering how you would be able to relate your results to papers like Letamagiuri and Weber, JFE 2014, where they show that the improvement in risk premium estimation basically comes from downside events.
yeah.
Because here you seem to be kind of agnostic. So you have a time variation in the risk premium, but it could be that you might be able to relate it to specific economic events, if that makes any sense.
Yeah, so I mean, right now we try to make it, as model-free. I mean, when you have seen the beta estimation, right, and then with the gamma, this covariance, we didn't want to specify any like conditioning variables. You're kind of saying, okay, eventually you still should go back. And I agree with you, because eventually when we want to understand this time variation in both risk loadings and premium, we have to go back eventually to that. But I think that's probably left for future work. But particularly with the downside risk, yeah, I don't know how to directly connect that to our setting here. But if that story is true, yeah, I'm not sure what implication it would have on the factor loadings or premia, the time variation. Yeah, but definitely interesting to understand how conditioning variables matter and which one.
So you mentioned that macrofinance people should, your paper contributes to macrofinance people that want to write down models. Do you have any sense of what kind of models, like in a consumption-based framework, give rise to these time-varying betas? So
Honestly,
I mean, a clue is this, like if you take any standard kind of model, like those beta loadings are going to be your preferences.
So I think a lot of the models have constant loadings and constant premium. I think some of the models actually do have
habit would be time varying.
Yeah, so some of them are time varying, but I don't know whether anyone has looked at what this time variation looks like, or what it, for example, implies for predictability. I think it's just a new dimension which people can look at, or a new set of restrictions which people should look at, because it seems in the data it seems very important, right?
So a second follow-up question is that people in equity literature have criticized these conditional models because they do a terrible job out of sample. And so people have argued they're pricing alpha through the back door. But when you try to actually just look at the outer sample R-squareds, they're a disaster compared to just multi-factor models. So you're doing things in a GMM framework, but have you tested, can you do an outer sample R-squared?
I mean, the main thing is the GMM, but we also do the thing where you stop at time t, you look at your estimate of beta, which is in real time and out of sample, and then we do a hatching of test assets, or hatching out dollar and carry risk using these betas, and that seems to then lead to these hatched test assets which have average returns close to zero.
You roll forward and do that in real time.
So it does seem to work actually quite well.
Okay.
Yeah. All right. Thank you so much.